Hi, ladies and gentlemen. This is Mr. Green, and this is another lesson in my series of Algebra 2 lessons. What we're taking up today is the concept of factoring completely polynomials. Completely factoring polynomials. It's 1.09 lesson. We're getting near the end of Unit 1, so there will be a unit review and test coming up quickly. So be prepared for that. Okay? So factoring polynomials completely. Well, here's the deal. When we have a polynomial that's to the degree 3, we know there will be 3 factors of it. Okay, that's what this is telling you right here. Every polynomial of degree n greater than 0 can be written as a product of n linear factors, 3 factors going into it. So if it's of degree 3, it would be 3 linear factors that were going into it. But sometimes we can't find those factors. For example, when you look at this one, x squared plus 25, and they want you to factor it. Well, you know what? You say, well, x squared plus 25 equals 0. That's we know where the factor would be. We get x squared equals negative 25. And we've always said, you can't do that. You can't square something and get a negative number. But, this is the very thing that caused mathematicians to go crazy. We know there should be 2 factors here, but we can't get them because they're negative. So what they did is they invented a new way of looking at the numbers. They said, well, if we take the square root of both sides, we're going to get x on this side, and we're going to get the square root of negative 25, which is actually x is equal to 5 times the square root of negative 1. And this is difficult to write. And it's not possible. It's not a possible number that we can come up with. So they started calling it the imaginary number. Imaginary. It means that it doesn't really exist. It's the square root of negative 1. And if I square it, I squared is going to be equal to negative 1. It's that simple. It really is that simple. So what we're going to do in this situation is we're going to say that x is equal to 5i. And that becomes an imaginary number. So what does it mean up here when it says complex numbers? Complex numbers are made up of all the real numbers and all the imaginary numbers. So in this situation, it would be x is equal to 0, a real number, plus 5i. That's the complex number. How does this look in a graph? Well, if you're looking at this on a graph, here, this one crosses the x-axis or y-axis at a positive 25 up here. And it opens up this way, like that. So we know there are no roots, but that's what we're looking at. We know that there has to be roots because it's an x squared term. And so putting these things together makes mathematicians just go crazy, and they can't figure it all out. That's why they invented these imaginary numbers. Okay? So here's the deal. Anytime we have a number that is a root of the polynomial, and it occurs more than once, it's called a multiplicity. Multiplicity means occurring more than once. If you look down here, we've got a polynomial, and they factored it for us, and you can see right here, x minus 3 is a factor twice in this particular situation. So what are we looking at? We're looking at x is equal to 3 is a multiplicity of 2, has 2 roots there. Okay? It has a multiplicity of 2. And so anytime you've got a root that occurs more than once, it has a multiplicity factor. And that's what we're looking at, and that's what we talk about with multiplicities. Okay? So finding, this one is talking about having something with a degree n, where n is greater than 1. It must have at least one complex root. And the corollary there has n complex roots as long as the roots with multiplicities are counted m times. So what we're going to do is we're going to do a little experiment. Okay? Over here we've got x minus 3. What is the root of this? Well, we set this equal to 0 and we get x is equal to 3. So where is my complex root in this situation? The complex root in this situation is going to be x is equal to 3 plus 0i. Okay? Still fits in with the zero property. Multiplying by 0 gives me 0, so I've got x is equal to 3i. That would be the complex root of this one over here. How about this one over here? How many roots are there going to be? Well, it's degree 5. That means there's going to be 5 roots, okay? And that's what we need to be looking at when we're doing these type of things. This one is saying find the number of complex roots in each equation. Because this is to the 5th power, there are 5 roots. Because this one was to the 1st power, there was 1 root, and there it is right there. Okay? It's in a complex root. That's how you're going to be doing these type of problems that you're looking at here. Okay, so how do you factor a polynomial completely over the set of complex numbers? First, you use the degree of the polynomial to determine the number of complex roots you're going to need to find. So you need to find out if it's to the 5th power, you got to find 5 roots. You identify the possible rational roots that you can. That's where we take the constant and divide it by the coefficient and factor it completely. See what all of our different numbers are. Use the rational roots in synthetic division, in division, or any other strategy that you might have. Find all the rational factors and factor them. Okay? When you get the remaining polynomial, you can factor the remaining polynomial. Okay? So, having said that, let's move forward here. This one is asking me to factor this completely and then to graph it. Okay? Well, looking at this, I see x squared, x cubed, x squared, x, and to the 0th power. That means we're going to take my possible factors, 8, 4, 2, 1, as -1, -2, -4, and -8. Okay, so I'm going to just pick one to start with. I always like to start with the number 1. It just seems like a reasonable place to start. 1, -6, 10, -8. Bring the 1 down. 1 times 1 is 1, plus -6 gives you a -5. Times 1 gives you a -5. That's a 5. 5 times 1 is 5. That gives you a -3. Nope, it's not a factor, but it gives me a point. I'm going to have 1 point here. 1, -3. Okay? Let's go to another one. I'll use -1 as a factor. 1, draw my line down here. Bring the 1 down. 1 times -1 gives me a -1. That's a -7. Times -1 gives me a +7. That's a 17. Times -1 is a -17. And -8 is a -25. So that gave me another point right there. -1, -25. Okay? Yep. Still haven't found a factor yet, so I'm going to keep going here. I'm going to use 2. Bring the 1 down. 1 times 2 is 2. That gives me a -4. That's a -8. That gives me a 2. 2 times 2 is 4. And -4 gives me a -4. Found another point. 2, -4. But I still haven't found a root yet, have I? Okay, let's try -2. Bring the 1 down. 1 times -2 is -2. That's a -8. That gives me a 16. And 10 gives me a 26. Times -2 is a -52. Minus 8 is a -60. Wow, that one's going out of bounds. And it looks like I don't think I'm going to get a root going that direction at all. Okay? So I'm going to stop going in the negative numbers there. I'm going to keep going in the positive numbers. So I'm going to try 4. Okay? Bring the 1 down. 4 times 1 is a 4, plus -6 is a -2, times 4 is a -8, and 10 is a +2, times 4 is an 8, and that 8 and -8 gives me a 0. I found my first root at 4. At 4, okay? So, what have I got left? I've got x squared minus 2x plus 2. Well, I can see from looking at this that it's going to be a 2 and a 1. let's see here, 2 times 1 is not going to give me a -2. I can't factor that. So what I'm going to do is I'm going to stick in here A equals 1, B equals -2, C equals 2, and my x values are going to be negative b, which is going to be a 2, plus or minus the square root of, well, that'd be 4, minus 4 times 1 times 2 is 8, divided by 2. So that's going to give me 1 plus or minus 2 square roots of -1. That's going to be 1 square roots of -1. So I'm going to have 1 plus or minus the square root of -1, which is 1 plus or minus I. Since I was looking for 3 roots, I actually have found my 3 roots. 1 plus or minus plus I, and 1 minus I. Those are my 0, 0. Those are my 3 roots. Okay? So if we were to want to sketch this one, to graph it out, okay, come back here, look at my points. 1, -3, so 1, it's at -3. There. I've got -1, positive 25, -1, it's a positive 25. It's way up here. I've got 2, -4, so at 2, it's at -4. And then I've got 4, 0, 4, 0, like that. So I think we're looking at something like that, right? When we know it crosses at -8, that's way down here. So it has to do something like this. I know. Ugly, 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 ugly. Try that again. Try that one again. Okay, -8. So I think it's going to go from here down to -8, back up, and like that. I think that's what we're looking at as far as the graph is concerned. And I'm doing that freehand, so it doesn't come out very good. That's what you guys can do. I mean, I'm not looking for perfect graphs when you guys are doing these things. I'm looking for you to be able to give me an idea of what it does. Notice here that we've got a couple of places here on the graph where it did not cross the x-axis, but we've got a couple of dips in the graph, right? It's not just a perfect squared graph, a perfect polynomial. Excuse me, a perfect parabola. It is got a little dip in it there, doesn't it? This is what you're looking at. That's where where one factor is. This other one over here, difficult to say. Okay? So I appreciate you guys when you're sending me K-mails and sending me voicemails and things like that, identifying the fact that you're in Algebra 2. It helps me find issues quicker and helps me answer your questions. I really look forward to seeing you in the next Class Connect, where I'll be working some problems and doing a review. Talk to you later.